Okay, I would like to start the lecture. And I want to start with one thing that we forgot so far, but which I want to add to chapter 11 on the optimality conditions, and which I will still write down tonight, and or a bit later, but it's chapter 11.5, something like this. And it will be about the sensitivities of optimal solutions with respect to parameters. Yeah, so parametric sensitivities. And it's, again, like for unconstrained optimization, regarding the problem where we have an optimization problem which depends on some parameters which we can change. And the question is, how does the solution depend on these parameters? And for constrained optimization, there are some interesting relations coming up here. But the general setting is actually exactly the same that we had before. Just that we have the function now depending on x and p. But p is not an optimization variable. And implicitly you might say that there is a p coming in, that's the data, then you solve a problem, and what comes out is an x star, which is a solution of p. But of course the question is again, does this map exist? Is it continuous? Is it differentiable? And so on, right? And the idea that we can use again, like before, to find out if this map exists at least locally is the same idea that we used for optimization, for unconstrained optimization. Namely, we look at the necessary optimality conditions and try to formulate an implicit function based on these necessary optimality conditions, and then prove that this implicit function exists because we can apply this implicit function theorem. So that's the only aim that we have. And so the question is, so to say, does x star of p exist in a neighborhood, at least, of something that we could call p bar with a solution x bar. So given is a solution, and the solution, the question is, if we perturb the data of our problem a bit, does the solution change with it? And the second question that we will also ask is, how much does the objective change? And that will be an interesting result in this context as well. Okay, but let's first make one assumption, and the assumption here is, or maybe I will try to first give the approach, and then afterwards we see that we need exactly one simple assumption. So the idea is, as we already discussed, but we can actually set up a root finding problem. We can actually say we define our variables w to be the x and the lambda together, yeah? And we define a big function, big F, of all these w's and also of p, which is given by the gradient of the Lagrangian with respect to x, which now depends, of course, on x and lambda and also on p, because we have these parameters, and it also depends on g of x and p. So these are the necessary optimality conditions, and they depend on the unknowns w, which are both the primal and the dual variables, and on the parameter p. And then apply the implicit function theorem to w star of p. And actually, of course, our aim is to set this f to 0. So to find for every p a set of x and lambda that make these equations satisfied. And so we start with a solution not only of x bar, but we will start with a solution a W bar which is given by X bar and lambda bar, which are a solution to the problem at P bar. So we have some values for P, which I call P bar, that's a fixed value. For that value we have a solution of the optimization problem, and at that solution this is a local optimum, so the first order conditions will hold, at least. So the theorem says, assume that P bar, X bar and lambda bar are given with first order necessary LICQ and first order necessary conditions satisfied at the point X bar lambda bar, but also and second order sufficient conditions. And that is the extra thing that we need to assume. Now maybe we call this problem, this is the problem, should I give it a name? I call it NLP, like nonlinear program, depending on P. At X bar, lambda bar for problem NLP P bar. So you state the problem for a fixed value of P, and you assume that you have actually a tuple of P, X bar and lambda bar given, which satisfies all the things that we need usually. So the linear independence constraint qualification would be satisfied, the first order necessary conditions would be satisfied, and also the second order sufficient conditions. So it is a local minimum. And the theorem says then a curve X star of P and lambda star of P exists in the neighborhood of P bar. That's the theorem, and you might wonder how we prove it, and it's relatively easy to prove it, and it will make use of one little lemma that I presented already, but I will restate it in a minute. But the idea is, of course, that we regard the implicit function W star as a function of P, defined by the root finding problem W P equals 0. So that is the implicit function that we use in order to define the W and as a function of P. And the only thing that we need to show is, first of all, that f of W bar and P bar is equal to 0. I should say that, of course, W bar is X bar and lambda bar together. I think I said that already, so I don't need to restate it, sorry. So this one is, of course, clear. That is due to the first order necessary conditions, right? These are the first order necessary conditions. So that will be satisfied. And then the other thing that we need to check is if the Jacobian df by dw at W bar P bar, if this matrix is invertible. That was the only other thing. So that's the second thing. Is it invertible? And in order to investigate if it is invertible, we need to compute it. And if we look at this question, if this expression here, then we see that this whole matrix, df by dw, and I omit the argument now, I will re-enter it if necessary, is just given by the second derivative of the Lagrangian in the top left corner. That's the second derivative of this. I can also differentiate that respect to lambda, and then I get here minus the gradient of my constraints. Here I get the gradient of my constraints transposed, if I differentiate that with respect to lambda, and if I differentiate it with respect to x, and if I differentiate the last line with respect to the second variable lambda, then there is a 0. So it's this matrix. And of course, this is invertible if and only if the symmetric version of that is invertible. So we could also omit this minus sign here, but just a redefinition of the variables. But the little lemma that we use and that I used already before is actually saying the following. It says that this matrix, the lemma, says, as I said already, matrix B, A transpose 0 is invertible if the rank of A is equal to M. Yeah? So M is actually A is a matrix which is composed of M columns and N rows. M rows and N columns. That's what I wanted to say. And B is of course a matrix which is N cross N. So this matrix is invertible if the rank of A is equal to M, and if Z transpose B times Z is bigger than 0 for all Z which are not equal to 0, but which have the property that A times Z is equal to 0. So that means actually all non-trivial members of the null space of A, for them the product with the matrix B should be positive. And this lemma is of course part of the exercise to prove, so I will not prove it, but it's a sufficient condition for invertibility. And the interesting thing is that this invertibility is exactly the same as, what is this? So we see that second derivative of L, and here we have nabla G, and here we have nabla G, and here we have a 0. This is really a special case of that lemma, and nabla G transpose, so the rank of this being equal to M is equivalent to LICQ. So we see that for this reason we need LICQ. The second thing is that if that this is positive definite on the null space of the constraints means actually that this thing times Z transpose Z bigger than 0 for all Z not equal to 0, which have the property that nabla G Z equals 0. This is exactly the second order sufficient condition. Together with the first order condition which we had already used. So we see that exactly the conditions of this lemma are met if LICQ holds and if SOSC. Actually I should, to be correct, so SO, second order sufficient conditions implies this, and also first order necessary condition. Okay, so in that sense we have already shown that these curves exist, and we can even compute the derivative if you want, but I don't want to give it. You can actually, you could compute the derivative, so one could actually get, I put it as a remark, so W star as a function of P can be differentiated with respect to P, and the solution will be the negative of this matrix, and then here we have df by dp, right? That is the usual implicit function derivative. So you could compute it if you want, but I don't want to compute it now. But it's even a differentiable function. So now there is a little interesting result which I also want to share with you, and it will answer the following question. So when you have these solutions, the optimal solutions changing your parameters, you could ask a question: how much does your objective improve or get worse when you change your problem. And that's what people usually call parametric sensitivities, and it's a relevant question that someone could ask. You say, I can solve all your problems, and then your boss says, but if I would change that parameter a bit, so for example, one cost value, so you say if I give more, if the price of electricity would raise a bit, how would this affect actually my optimal solution? Yeah? And then usually the person would not be interested in just knowing how would the parameters of the solution of the problem change, but maybe more interesting would be how much does the value of the objective change? So how many euros do I lose if the price of electricity increases, for example? Always assuming that you can make the optimal solution. And so another interesting question is, how does actually F change under the perturbation? So the question is also, how does F of x star of p, comma p change? And this is what I want to investigate briefly with you, and it can be done quite elegantly using the Lagrangian function. And as you will see in a minute. So this theorem says, it's a very simple thing. The total derivative of f of this thing with respect to p, I mean of the function, and I should really put it here in the top, x star of p, comma p, this whole derivative, the total derivative, is can be obtained as the partial derivative of the Lagrangian at x star p, comma lambda star p with respect to p. Sorry, this also the Lagrangian depends on p. Right? So this is exactly the Lagrangian that we always use as the Lagrangian. And the beauty of this is that you don't have to differentiate your Lagrangian with respect to anything else than with respect to p. You don't have to go through the effort of computing this whole derivative and then plugging it into the function f and so on, which you could do, but you can get the answer much quicker, and you can see it basically from your solution very quickly. And so this is an interesting theorem that I want to prove. And sorry, I made the same assumptions as before, under the same assumptions. As above. This is part of the theorem, of course. And what we will use is the fact that the Lagrangian at the optimal solution, lambda star p, comma p, is, of course, it's given by, I can just state it again, it's actually x star of p, comma p, minus lambda star of p transpose times g of x star of p, comma p. So that is the detailed expression for the Lagrangian. Maybe I've moved this further and this a bit higher up. And if I made something wrong, say it directly.
The minus sign in the matrix.
Sorry?
The minus sign in the matrix.
In that matrix, yeah.
And why is it not
okay, I just so this matrix is invertible if and only if the one with the minus sign is invertible.
Yeah.
So that's what I use here. So I need not to check the one with the minus sign. But of course, in the implicit function theorem here would be the minus sign. If you want to be correct with this notation of f. Okay, so I will use the fact that this is actually always 0, right? Because these are all feasible solutions and they satisfy that this whole thing is 0. So I know that actually I could, instead of computing the total derivative of f, I could also compute the total derivative of the Lagrangian. So I have actually already established with this thing that df by dp, I omit all these arguments, is the same as the total derivative of the Lagrangian with respect to p. Because they are the same on the feasible points, because I just add 0. But now I want to use another thing, and for this one, I think I will just do it the detailed way. The first thing is I will just use the outer derivative and then the inner derivatives. Yeah? So what I can do is I will compute the Lagrangian with respect to x and then x with respect to p. So this is actually depending on 3 arguments, so I need 3 partial derivatives, so it's dl by dx times, and here I write the total one, dx star by dp, so that was the derivative that we had here, one part of it actually, plus the Lagrangian with respect to lambda times the lambda star divided by dp. That is the other part of this, what we get here, and then plus d Lagrangian by dp, the partial one. So I think you agree with all these things. But now, what is now the beauty of this? So this is of course all evaluated at the optimal solutions. And what is this? This is this thing transposed, right? But at the optimal solution that will be 0. What is this? dl by d lambda. If you look at what this Lagrangian, it contains the lambdas here. If you differentiate it with respect to lambda, then it gets exactly again, this will be equal to minus g transpose. And that is, of course, also 0, because we are at an optimal solution. So whatever these derivatives are, we could compute them, but if we once decide we take the Lagrangian instead of the function itself, they will be multiplied with 0. And these are finite numbers multiplied with 0, that is definitely 0. So we get, the only surviving term is this. So it's dl by dp, the partial derivative evaluated at the point where you are. But you only need the partial derivative. And that's quite handy, because it's much easier to compute a partial derivative and you don't need to look at all these quantities here. I don't want to give many examples, but I want to make one specific example that is interesting, and I will directly formulate it as a corollary. And this is that if you regard the following problem, where you have your optimization problem is just something which depends on x, and x is a decision variable, but there is a constraint, and your constraint is p plus g of x equals 0. So it has a very specific dependence on your parameters, and you have a solution given with p equals 0 and x star and lambda star. So this is given. So you have basically a solution that is given, and you want to ask the question, what happens if I perturb my constraints a bit? And that could, for example, if you have an equality constraint, you say, for example, I want to, let's say, throw a ball and with minimal effort or whatever, and I want to throw 10 meters, and then with this parameter dependence, you could say, what happens, how much more energy would I have to spend if I have to throw this ball 10 meters and a centimeter more? And then you could actually, then you would be interested, how sensitive is your solution to this change in your constraints? So instead of 10 meters and 1 centimeter, that would impose some extra cost, or it would give you a gain, and depending on your previous solution, that you can actually find this gain quite quickly. And the answer is actually very simple. Then f of x star of p, and the total derivative of this whole thing by p is given by, so it's actually a partial derivative of a scalar function. It must be a lying vector of the dimension of p, but p has the same dimension as g, and there is a vector in our whole thing. And it turns out that the partial derivative is given by lambda star transpose. So the beautiful answer here, and I will prove it in a minute, is that the cost That if I want to ask how much do I gain or lose when I prolong my constraint that I want to meet by, let's say, an epsilon, by 1 centimeter more, that then actually the multiplier itself of this constraint tells you of how much your constraint will be improved, your objective will be improved or not. Yeah? So that is what people sometimes call multipliers as shadow prices. So that means actually that a multiplier gives you the cost of a constraint. So a constraint, if you relax it in one direction, you will gain. If you make it move it in the other direction, then you will lose. But how much you will lose and gain will depend on your constraint multiplier and on nothing else. And the proof of this is extremely simple, and it's just based on this theorem that we have just proven. So I will just use the formula, and I will just compute the partial derivative, of the Lagrangian with respect to p at the solution. But what is the Lagrangian of this? It is actually the partial derivative of f with respect to p minus so maybe I first define Lagrangian is f minus lambda transpose p plus g, right? So that's basically what we have. And so then here I get minus lambda transpose, that's this partial derivative, and then minus lambda transpose dg by dp. So that would be the plain way to write it down, but now because of this special setting, f does not depend on the parameters, g does not depend on the parameters, so this thing and this thing will be 0, and the whole thing will be minus lambda transpose, and you see I made an error in my theorem, it must be with a minus sign here. But still, it's very nice. This depends. Actually, you could also put a minus sign in front of the p, and then there would be no minus sign here. So in this case, don't worry about the minus sign, but this is the result that I wanted to share with you. So the multipliers give you the cost of your constraints, basically. And I find that a very important and useful interpretation. And I want to note something, that if you have f and lambda 1 times g1 and lambda 2 times g2 up to lambda m times gm, these things, they all are added in the Lagrangian. So f plus all the lambdas multiplied with each of the g's. So if you add these things, they need to have the same units, and they automatically will have the units which are the same. But your objective might be, for example, $. Your constraint might be cost of electricity is also maybe $, or something. Let's say it could also be a constraint that says so much meters. So I want to reach exactly 10 meters by throwing a ball or something like this. And then the unit of your multiplier must be, by definition, $ per meter. So it actually makes complete sense, also from a unit point of view, that if your objective was $, and your constraint was in meter, then the multiplier must have the unit $ per meter, and that's exactly what is reflected here. It actually gives even a quantitative answer. It says that the multiplier is not only having the right unit to say it's how much $ per meter do I gain or lose, but it's also exactly giving you the amount of things that you gain or that you lose in the optimal solution. Okay, so the note is here, they have the same units. So this is some part of parametric sensitivities I think it's important to share with you. The general part is relatively analogous to what we did for the unconstrained case. I mean, there is just the extra catch that the the conditions that we need are linear independence constraint codification, first order necessary conditions, and second order sufficient conditions. Actually, I just realized second order sufficient conditions, they cover also the first order necessary conditions. So I could actually leave that away in the assumptions, and I will when I write it down. So it's very similar to the unconstrained case where we also had just second order sufficient conditions, and if they hold, then this whole thing was invertible and we could have a solution map. It got a bit more involved because we had this funny matrix here, but it's not a big change. But what really is interesting, I would say, or useful and different and not existing for the unconstrained case is this thing. This partial derivative property, by the way, also holds for unconstrained problems. So actually there the total derivative can be replaced by the partial derivative of the objective. That's another, follows the same argument. But this corollary is maybe the most interesting part, conclusion of it. So the implicit function not only exists, but also if you insert it into the function, the objective function, and you look how this objective function changes when you perturb your solution and your problem, then the change is exactly given by the multipliers. So I wanted to either continue with an example of this, if you want that, or I would like to make a short break to then start with the next part of the lecture. Do you want some example on this? I mean, of course it will be, this is already a kind of example, but we could have something with numbers if you want. Not with numbers, but with functions in 2 dimensions or something. If it's not needed, you want it? Okay, engineers want it. We will make a small example, okay? Yeah, it's very simple. I make a one-dimensional example to make it very quick. So I just do a minimalization of a number x, and I say, for example, that x should be equal to p. Is that too simple, or is it okay for you? No, that's too simple. I do x squared. Okay. So this is my optimization problem. Okay? And yeah, maybe I do, and I regard p bar is equal to 1. Yeah. And I want to compute how the solution depends on, okay, this is too simple, right? It's a bit too simple. Maybe we do something slightly different. I do an x1 and an x2. X1 plus x2. And here I add up x2 and x1. Okay? And then I have x element in R2. So then it's a bit more interesting. Yeah, and I have p bar equals 1, so I want to look at the solution of this problem at p equal 1. This is an example which goes actually through all the necessary and so on optimality conditions, so I could actually try to find a solution of this point which satisfies the optimality condition. So let's first state the Lagrangian. And I put this with a minus sign and with a equality here, so then I know what sign I need to have here, and then I have a lambda, and I have x1 plus x2 minus p. And I can now set this Lagrangian to 0, and I will get 2x1, 2x2 from this part, and then minus lambda from this part. And I can also compute the Lagrangian. This is the solution with respect to x, the derivative. I can, of course, maybe first compute a solution because I want to get a example solution. So my aim is actually to find x and also lambda star. So what are the optimal values here? And the constraint, of course, should be x1 plus x2 minus p, or minus p equals 1. And now I have a linear system of 3 unknowns, x1, x2, and lambda, and I need to solve these 3 equations together. That is actually what gives me my x1, and I think we will be able to find the solution. I guess that both need to be equal anyway due to symmetry. So I guess that both being 1/2 would be the right solution. So I think that x1 equals 1/2, x2 equals 1/2, and lambda being equal to 1 would be the solution. Is that right? 1/2, 1/2 minus 1. It's not right? Yeah? Okay. Okay, at p equals 1. Okay, so then I have some solutions, and what now this theorem says is that I can also compute the partial derivative of my Lagrangian with respect to p. But what is the partial derivative of my Lagrangian with respect to p? It is actually minus lambda minus p, so it will be actually equal to p. No, sorry, it will be equal to lambda. That's just what we had. It's up to a sign. It's actually this case. Yeah, the interesting thing is when we change this parameter p, and we know that the f of x star of p, this derivative with respect to p, when we evaluate it at p equal 1, is equal to 1. So we got an answer which was a bit interesting in the sense that our original problem, if you want to visualize it, it's relatively easy. It's x1, x2. The solution is something, this is the set where x1 plus x2 minus p are equal to 0. Yeah, that's the set that where these two things add up to p. So x1 plus x2 equals p is actually describing such a line, and if you increase p then you move it up, and if you decrease p then you move it down. And the objective function was actually penalizing all deviations from the origin. And what this theorem says is if you track the optimal solutions, I mean if I move this, this is for p, p dot bigger than 0, so then I move p, so to say, in time. If I move it in this direction, then my optimal solutions in this case will be very simple. I think they will just move along this middle line here. So these are the optimal solutions. So this is the path x star of p. It's a relatively boring path, I should say, but that is the solution path. The multiplier path will be a bit more difficult to describe. It's actually 2 times that thing, so it's also the multipliers will also increasingly grow. But the interesting thing is at the reference solution at which we are, when we move the constraint with some epsilon to this side, so if we increase the p a bit, then the objective at this value will also increase with epsilon. So that was a number example. Happy? Okay, good. Okay, so yeah, of course, it gets much more interesting when we really have units and more complicated examples. But basically, when you call an NLP solver and you get back multipliers, you know that your multipliers are the cost of the constraints, and that they have the units which are actually the complementary units to the constraint themselves. Complementary with respect to the objective. So please think of this thing. And one other thing that is also very logical if you think of it twice, but I just want to say if you would rescale your constraint, and you just say I want that this function is equal to 0, and then you say instead I want that 1,000 times this function is equal to 0, that's the same constraint set, right? But the multipliers will be reduced by a factor of 1,000 due to the sensitivity result. So the product of a multiplier and a constraint will be something of the same unit of the objective. So in that sense, multipliers and constraints have complementary units, and they belong together very closely. Yeah, so that was still part of the optimality conditions chapter, but I think I forgot and I wanted to still add it, and I suggest that we now do a short break of 10 minutes and then continue with the algorithmic chapter. Okay, so then I want to continue with the algorithmic chapter, and we derived already a few things in the last lecture. So we're in chapter 12, and what we got last time was already a statement that said that if we actually do a Newton optimization method, that we could also interpret it as a quadratic model, a sequential solution of basically quadratic programs. And this is one thing that I want to recall, because I think it is important. So Newton for f of w equals the Lagrange gradient and the constraints is equivalent to solving QPs sequentially. And which are the QPs? The QPs are the QPs where you have where you get the new iteration actually by minimizing all over all x subject to the constraints which are evaluated at the current iteration with a Taylor series x minus xk equal to 0. And as in the objective, you could actually take the gradient of the objective times x. Now it's a matter of choice if I subtract this constant term. It doesn't affect the next iteration, but anyway, I do it here. It looks like a first order Taylor series. The constant value also doesn't matter, of course, so I can omit it, but I can also write it, so I could just say this is like the constant value of the objective, the zero order term, the first order term, and then you would expect a second order term in the objective in order to make something meaningful and quadratic. But the second order term is already involving the second derivative of the Lagrangian. And that is the important point here. So it's not the objective, but it's the full Lagrangian which matters here, and evaluated at xk and lambda k. So this one is an optimization problem which depends on xk, and it also depends on lambda k. So these are the quantities that you put in, and what you get out is an x qp, that is the solution of the qp, and the lambda qp, and they can be taken as the next linearization point, and you get a loop, and then you have a Newton type method. And this is absolutely equivalent to just applying Newton to the system. Yeah, so that's a bit interesting. And I prefer this formulation where I get the absolute values of x and lambda out of this. In the Newton method, very often you work with the increments, the delta x and the delta lambda, but that's just a transformation of an additive change of variables, right? So that's nothing important, but this is in some sense an approximation to your optimization problem based on first and second order derivatives. And the interesting thing is that you need the first derivatives of your constraints and of your objectives, and the second derivative of everything together, but not the second derivative of the constraints separately or of the objective separately. And that's a useful fact. You need only to implement one Hessian and not several. The other thing is that if this Hessian is positive definite on the null space of these constraints, then that means basically the reduced Hessian is positive definite, then this problem is actually a convex QP, and you can solve it easily to global optimality and so on. This would not be the case if I would have quadratic terms and these constraints hidden. Good, so this was so far so good. We already introduced one specific method which would be a particularly interesting variant, and that was the generalized Gauss-Newton method, and that is chapter 12.5. We call it the generalized Gauss-Newton method, or GGN. Sometimes it's also called constrained. And then you would abbreviate it CGN. And this method is only applicable for a specific form of objectives. It's something where we have an objective given as a least squares sum, so it's an optimization problem of this form where we have 1/2 and then the Euclidean norm of a vector valued function big F, and subject to constraints. So that's the problem that we want to solve and which we will solve with a Gauss-Newton type algorithm. And the Gauss-Newton idea was actually to linearize the nonlinear functions, but not to linearize the quadratic norm. That's the basic idea of the Newton method, and we can apply it here. So you can formulate and solve QPs. And these QPs would be based on a linear expansion of both functions, and there are different ways to write it. And now I maybe just for fun I will write today the other notation. So here I have a Taylor series of F. I put it again into this norm, and then I have here a Taylor series of G. xk plus nabla G of xk transpose x minus xk equals 0. And that problem I can formulate, I can solve it. It's again a quadratic program. If I multiply this out, it will be a quadratic program. And what you will see is that what I need to put in, and maybe I move it like this, what I need to give in order to be able to formulate that problem is actually xk only. And then this problem can be solved, and it gives out a xqp. So this, the solution of the qp. It also can give out the multipliers if you want. No, so they are part of the linear system that I need to solve. But it turns out that the multipliers are not really memory of this method, because it just needs the xk. So there's no way the multipliers enter here. So I want to xk plus 1 and so on. They are the memory of the algorithm of GGN, but not the multipliers. So in that sense, it's a funny method. It's a method which is completely multiplier free, if you want. And one could actually even never look at the multipliers and still have a valid method here. So that's something I want to point out. What is, of course, dubious is if this method will converge at all to the optimal solution and so on. You remember, for unconstrained problems, we have shown that it's possible to make Newton-type methods work with inexact Hessians. And that's what we also do here. And I want to tell you what this is. So the QP objective, what is it actually? It is this 1/2 thing, but what is it if we multiply it out? It will be this term. It will be the mixed term, and it will appear twice, so the 1/2 is dropped. What we will get is actually x minus xk. Then here we have the nabla big F of xk transpose, and that will be multiplied with the f of xk transpose. Okay? And then you get here a quadratic term which will be with the 1/2 x minus xk transpose, and here you have the nabla f transpose, and x minus xk. So the interesting thing is that this exactly is the objective gradient of the little f at xk transpose, because we did that before. We computed the gradient of the least squares objective, and the gradient was actually given by, if f is equal to 1/2 big F squared, then nabla f was given by the Jacobian transpose big F, right? So that's what you remember. And the Jacobian is just the transpose of this gradient, big F. So it's exactly this expression here. So what we got already is that the gradient is the same here. This is a constant. So we have a constant plus nabla f of xk transpose x minus xk. That's all fine. But then here we get actually 1/2, and I will call this matrix B Gauss-Newton at xk. That's actually what it is. It's just a definition of that. It's not exactly the Hessian. So in order to analyze this algorithm, we could just see, okay, this is with a wrong Hessian. But a wrong Hessian is something that usually does not affect our Newton method. If you remember what we used in order to derive these problems was only, at some point we replaced the gradient of the Lagrangian with the gradient of the objective. And there was something that we used in order to make this a replacement possible, and that was that we have the exact Jacobian. But we didn't use the fact that there would be an exact Hessian. So actually what we can think of, so this is actually using the right gradient, but inexact, it's an inexact Hessian. So it will boil down, if you translate that, this is a quadratic model interpretation, but you could now do the translation back into the Newton type framework in this FW, and then it is actually equivalent to the following, to a method which has an iteration matrix which takes the Gauss-Newton Hessian here at xk, at the current iterate, has the right computed gradient here, has the negative nabla g xk transpose here, and a 0, and applies this to delta x, delta lambda, equal to minus the gradient of the objective, of the Lagrangian, and the residuals. So that was the Newton system that we would solve in this method. And due to this, actually, this trick that we replaced the delta lambda with a new lambda, which was only depending on having the right Jacobian here, we could replace that with a gradient of your objective. You remember that trick? And that way our Newton system would be completely independent of lambdas. And that's actually what we do here. So this was equivalent to just solving B Gn of xk. Here we have nabla g of xk. Here we could actually, I will now use already the positive multipliers because it's a bit nicer. Actually, here's a transpose and not here. 0. And here I have I can use x minus xk. That's a delta. And here I use lambda qp. So that's a new multiplier equal to minus. And here I use now directly nabla big F of xk times f of xk. That's a big one. That's the gradient of the objective. And here I have g of xk. So this is actually what I do. And it's completely equivalent. The new x, this delta x is equal to x minus xk, and delta lambda is equal to lambda qp minus lambda k, if you would like to have a previous lambda. But what you see here is that because every single thing of this Newton system does not depend on lambda, and the only memory of your system is actually the xk, this implicitly actually is an iteration in xk only, because you get the new x out of this system, and at that point you relinearize your system again. You get your new matrix, your new residuals, and you get a new x. So actually the lambda is just some helper variable here that will be forgotten after each iteration. But that was not my point. This is actually equivalent to the QP that I've written down up there. So that is the necessary optimality conditions. Sorry, here it was a minus sign. the necessary optimality conditions of that QP are exactly these. This was equivalent to this system. Yeah? Now I'm doing reverse engineering. And this system was just a Newton-type method to solve the root finding problem to make this 0, but with a matrix which is not exactly the right matrix, because this is not the second derivative of the Hessian, but it's the second derivative. It's an approximation of it. So we have again, like previously, a wrong Hessian, an inexact Hessian. So the inexact Hessian. And we know that if this Hessian would be exactly close to the second derivative, then we would have quadratic convergence, and if it's not, then this whole iteration matrix will be a non-perfect matrix, and we will get linear convergence, right? So the important question is now, how different is this matrix from the exact Hessian? That's what I want to analyze here. So how different are the second derivative of the Lagrangian at xk and lambda k and bgn at xk. Now, of course, it's difficult to assess it because we don't even know the values of the multipliers in the Gauss-Newton method. We throw them away anyway. Yeah? So what is so maybe why are we interested in this? This determines the linear contraction rate. For the Newton type method. And you remember this was what we called kappa. If you remember, what we had in this kappa condition was actually, if you think of this Newton type iteration, was something where you had a big F, you wanted to bring it to 0, and then there was something where you actually needed to compare mk to the -1, and then we had here mk minus the real Jacobian, that is, oh, now I see that things are really getting mixed. This F is, of course, not the same as that F. You see at the top, I have 2 times F. That's really nasty. One F has a very different meaning than the other one. And now I refer to the left one, the general Newton type thing. And then it's this F. And the variable of it is W, of course. So this norm is what we wanted to be small. Yeah, so this is what we wanted to be smaller than kappa. Remember, that was one of these conditions. And so it's basically the difference of this and that matrix. And for Gauss-Newton, what we will have, or for generalized Gauss-Newton, we will have mk being this matrix bgn of xk, and then here the nabla g and the nabla g and the 0, while the exact df by dx by dw is given by the true second derivative of the Lagrangian, and here actually we can put a minus, that doesn't matter. So what you see immediately is that we use exactly the same derivative, so actually the difference is only in the upper corner. So actually mk minus the d big F by dw is equal to a matrix which actually gets a bgn minus the second derivative of the Lagrangian, and all the other entries are 0. Yeah, so the only difference, the only error that we make in our iteration matrix is actually in the upper left corner, and that's why I'm interested in this difference, because this difference will determine my linear contraction rate. And in order to make the analysis simpler, regard the asymptotic rate convergence to a solution which is completely hypothetical. We don't know it, right? But I just have a solution x star lambda star of my optimization problem. And you remember in one of the appendix lectures we gave that this linear convergence rate would depend for a method that we had on this matrix, where we had the approximate iteration matrix evaluated at the solution. So this is actually W star, so this vector of both variables together, minus d big F by dw at W star. So this was the iteration matrix that we used in the asymptotic analysis, and it was the spectral radius of this which matters, and which is actually the asymptotic contraction rate. You remember that theorem? Yeah, that analysis that we did. So we can actually look at the solution itself, and at the solution we look at the difference between these two matrices. And now there is an interesting claim that I want to do. It's actually let's formulate it in form of a little theorem to formalize it correctly. And what I claim is actually that this rho is proportional to, actually I can just say it, it's equal to the order of the objective at the solution. So, no, it's even, sorry, it's different. It's the order of this, of the norm. It's not yet squared. So that is, let me think a moment, yes. That is what I want to prove. So it basically says that if I have a very small objective value, that my Gauss-Newton method, or the generalized Gauss-Newton method, will converge very quickly. And if I have a large value, then it will converge not so quickly. Of course, it's a bit strange to put the objective value into an order, because it assumes that I can change the objective value, while usually we take this problem to be fixed. But let's assume that we have a problem which is, for example, depending on measurement data, you want to fit a trajectory to some data, and if you start with a perfect fit, and then you perturb your measurement data to the real ones that you got, then you basically enter in this field where you change your optimization problem, and your Gauss-Newton method will perform extremely well at the moment that you have a perfect fit. And when you make it bigger and bigger, these residuals, because you take the realistic noisy measurements, you make your residuals bigger and bigger, and the convergence rate of your Gauss-Newton method will be worse and worse. And so let's try to prove this. And I want to actually just regard at the difference. I mean, this matrix is invertible and so on under nice, assuming LICQ and second order sufficient conditions, so that all these things are nice and bounded. And so now I want to compute at this difference. Regard m of W star minus df by dw at W star, which was actually this matrix. It was and I think if you don't mind, I will from now on use a big R here, because then the whole notation thing will be resolved. So I just make a quick R posteriori change. This is an R residual, okay? And then this is also an R, because otherwise, so R is a function of X, big F is a function of W, which is both the multipliers and the primary variables. So because otherwise I think we will get all completely confused. So is there another F which I need to change here on that side? Here at the top. So here an R, here R. Fortunately, R and F are not so different. Okay, here's an R, and I think that's it. Okay, so now I'm happier. Sorry? One left here, right? Did you mean that one? Or yeah, good. Perfect, thank you. Okay, and here I actually mean the residual itself. So the thing that we want to minimize is if it's small, if we have a good fit. Yeah. Maybe before I prove it, actually I make a remark. If this thing is small, that means actually a good fit. If you think of what we had in Gauss-Newton. And so we look at this difference, and so the difference is actually the Gauss-Newton Hessian, which is nabla R times nabla R transpose minus the second derivative of the Lagrangian. Yeah, so if this would be 0, then I would be happy. But I want to actually just show that this matrix is of order R residual. So what we want to show is only the thing that this matrix will be 0 if this thing is 0. Show that this thing R nabla R transpose minus the second derivative, all at the solution, that this matrix in any norm is equal to this order of R of X star. That's what I want to show. And in order to show it, I compute actually the second derivative of the Lagrangian. So what is the Lagrangian function for this problem? It's a function of L, X, and L. It's actually having 1/2 then this Rx second derivative minus lambda transpose G of X. So that is our Lagrangian function. We are happy and yeah, everything is fine, right? But now we compute its first derivative. And its first derivative is with respect to X only. And what will it be? It will be the collection of Ri of X times the gradients of Ri of X. I going from 1 to, we didn't define how many residuals we have. Did I define that number somewhere? I think I don't. So then it's not M because we need that. Maybe let's call it Q, okay? So we have Q residuals for the optimization. And this is actually the factor 2, 1/2 cancels with a 2, and then I have this linear combination of the individual gradients actually. So that's the objective gradient. And then I subtract from it the sum from J equals 1 to M of our lambda J times G J of, the gradients of the G J of X. So this would be the first order derivative of our Lagrangian in detail. Yeah. By the way, this term, this is now each component, so these are scalar and these are standing vectors, so everything is a bit more standard notation than for example, what I use here. Here, the nabla R is of course a whole matrix with all these matrices, all these vectors next to each other. So now, but this is a nicer way to compute the second derivative, because the second derivative now is given by, it's the same thing that we did before, so here we need to compute the second derivative, but it should be a matrix of the right dimension, and it will be nabla Ri of X times nabla Ri of X transpose. So this is actually where we take this derivative and then make it a matrix of the right dimensions. But we also have the other term where we take the second derivative of this. So it will be plus the Ri of X times the second derivative of Ri of X. So that is what we had. And then we have the second derivative of this, and I don't save time here, space. It's the second derivative now of the G J of X. So until now I think you are all happy, I hope. But it turns out that this thing is again, that is the Gauss-Newton Hessian at X, and then plus this term and minus this term. So the difference is actually here. So I only need to look at the difference. And the difference is something that I want to now prove that it's of order. So maybe I give a definition of this whole thing. Yeah, actually I don't need to define it. It's the difference of nabla square minus gn, right? So I can also just say what I need now to show is actually that this thing, minus b gn, that this matrix is of order R, the second derivative of R at the solution. That's what I want to show, as we did for the unconstrained Newton method, Gauss-Newton method. And for this term, it is clear actually. For this thing, Ri of x star times the second derivatives of Ri at x star, it is obvious that this is of order R of x star. Yeah, I mean it's just linear in this, so it's definitely of linear order of that, just multiplied with that. So that's fine. This would be linear in R if we could show, and this is of course at the optimal solution, so it will be evaluated. So what we need to show is just one thing, and that is that lambda star is also of order R x star. And if we have shown that the multipliers themselves are also getting small, if your residual is getting small, then, because they are entering here in the similar way as the R's, then we are done. Okay, so this is what we need to show. And this is where the argument actually gets not complicated, but the statement needs to be made more precise. When I say order of something, then what I mean here is actually I implicitly think that I have a parametric optimization problem, and I could actually apply my parametric sensitivities to the whole thing. So what I assume, I regard a parametric version of this whole thing. Yeah, so I think I regard the problem where I have minimizing not just the objective, but I have the objective perturbed with a parameter p. In order to be able to compute some parametric sensitivities, and I will really assume, actually we could maybe make it even more complicated. I do it like this. So more general, and assume that R of x, that R of x star, and no, that's not what I want. Assume a solution for P bar, which is given by x bar and lambda bar, with R of x bar and P bar being equal to 0. So you could always achieve that by just subtracting the residual, but I basically assume that there would be a whole class of parameterized problems which have the property that at the P bar value, that's like the starting point, I have a 0 residual, and then I change P, and then I make it like a different problem. And what I want to show is that what I want to show is that lambda star as a function of P is getting order of P minus P bar. Yeah, because then it's of course also, I mean R is also, because R, yeah, so that's actually just a parametric sensitivity result, and yeah, it would be, it's actually a more precise statement of what I mean by R the order of R of X star, because actually if the problem is not changing, then I don't need an order, then it's just one number. So I need to have a full problem class where I start actually where this thing is 0 and then I make it bigger. And in order to bring it into the setting, I will introduce a parametric problem. But I think I just want to say e.g. Perfect measurements. So perfect measurements in the sense that they are perfectly fittable. Yeah? So that would be at P bar, and maybe then your vector P perturbs all the measurement vectors. So P could be a large vector, so it could perturb everything and make it different, and then you see that your parameter is I think it's probably getting everything is cleaner if I don't make it this way, but I just really make it with this formulation, plus P. So I perturb my problem so that I get a perfect fit. It's a possibly very unphysical perturbation, but anyway, it's something that I can always do, and then I think it's more logical. And then you immediately also see that the P is of the order of my residual R. Does that make sense? I will see actually. So the point is, if I make it more precise, so we regard a parametric problem and we start with a value where actually this is a solution. So at this point we have second order sufficient conditions, gradient is 0 and so on, and the P bar is made 0. So the residual of that whole thing is 0, and at that point we will actually look at the solution, and I will show very quickly one little thing which is very easy, and namely that at this point, so we have LICQ and second order sufficient conditions which assumes stationarity. And now the interesting thing is, what is lambda bar if I make this assumption? And the lambda bar will be determined by the optimality conditions of this problem, but the optimality conditions of this problem will be given by the gradient. So what is the Lagrange gradient of this whole thing? Or maybe first let's write down what's the Lagrange gradient. The gradient of the objective is 1/2 the Lagrangian is Rx plus P plus lambda transpose G of X. So that is our Lagrangian, and then the Lagrangian gradient is in this case I think it's getting complicated. I think it would be even profitable, and this can be done with any coordinate system. I will just say, to make it simpler, I will even say P bar is equal to 0. Yeah, then I will not be needing this P bar. Then everything will be a bit easier. And so now I can compute the second derivative of this, the first derivative of my gradient, and it will be, here is a minus sign, sorry. I will get the sum of all these things, but they depend on x only via that. So I will get the same argument as before. It will be Ri of x plus P times the gradient of Ri, and then minus the sum of the lambda j's times the gradients of j. Okay? And of course this will be 0 at x bar, lambda bar, p bar. And So now, I said that at the solution, this thing, at the point where I want to start with, by this assumption, I want to start with actually a zero residual. So that will be zero at this point. So that implies that this whole thing here is zero. And that implies that the linear combination of the constraint gradients is zero. But because they are linearly independent, because we have LICQ, so this whole thing implies that actually the linear combination of lambda j times nabla gj of x bar is equal to 0, and that implies that the lambda j, or all the lambda, this is actually the lambda bar, must be 0. So because of LICQ. That's exactly what it says. Actually, linear independence constraint qualification says any linear combination of the constraint gradients can only be achieved with, if it is 0, then the multipliers must be 0 as well. And so that's actually what we got here. We got already that the lambda at the solution which has a 0 residual is 0. So when we perturb the problem a little bit, it can only grow, and because of its differentiability properties, it will be order of the perturbation of your problem. So what we could always achieve here is, so to say, when you start, you have a fit. You could actually now subtract your residuals from your measurements, so to say, in order to get a perfect fit. And in this, for this perfectly fitting problem, you would get a 0 residual. And interestingly, for that 0 residual problem, your Gauss-Newton method would converge quadratically. And only if you start to make your residuals again the original ones, then you get this linear convergence, but it is of the order, so the contraction rate is of the order of your residuals themselves. So the main point is not only the residuals, but also the multipliers get linearly bigger if you make if your objective function is getting bigger. Okay, that was a long and a bit tedious analysis, and I'm sorry for maybe some iterations while we were on the blackboard. But I think that's enough for today, and the main message here is that the Gauss-Newton method that was so interesting and useful for nonlinear unconstrained optimization can basically in the same way be used for constraint optimization. It's again, or in this case, it's a multiplier-free method, so you don't need the multipliers in your memory. Yeah? You could actually, just have a primary variable x as an initial guess, and then you linearize. You can either formulate it like we did here, like that's the thing that I think is easiest to remember, but you could also, in practice, actually solve linear systems of this form. No? So that would be the way to implement it. You just invert these KKT matrices. But the thing to remember when it will be fast and when it will be not so fast is exactly the same as in the unconstrained case, namely when you have a good fit, it will be a good fast converging method, and if your fit is not so good, so if your residual is big, then your method might be slower or not at all converging. All right? But if you have a perfect fit, it will be perfectly contracting. That's what I wanted to share with you. Okay, thank you very much.